Hi there, Mr. Holcomb here with another episode of The Math Behind the Modules. Welcome to Lesson 5, Points of Concurrencies. Alright, concurrencies. What in the world is that? Alright, so let's start with a definition. You don't need to write this yet. It might be in the lesson further, but I want to start with it so we know what we're talking about. So it says three angled bisectors of a triangle intersect at a single point. The point of concurrency of the angle bisectors is called the incenter. And then if we take the three altitudes of a triangle and they're constructed or are concurrent, then the point of concurrency is called the orthocenter. So if you look at these diagrams here, they drew a line segment that is a bisector of each side to the angle bisector, and that is going to give you the orthocenter, or the point of concurrency. Okay, so opening exercise. You need a makeshift compass made from string and pencil. Hopefully you have that. I can't do it on a video, so I'm going to use my electronic compass, and we're going to use just the compass to do this. So what does it want us to do? Perpendicular bisector. So I want to cut each side in half and draw a perpendicular. Alright. So first of all, let's label these up. So let's call this angle A, and this one angle B, and this angle C. Then I'm going to take my compass, and I'm going to put the point right on A. Open it to B. As close as my program allows, and draw a circle. There is a circle centered at A with a radius of AB. Then I flip my compass around, and I put my compass point at B, and then I'm going to construct a radius of a circle centered at B, radius, length, BA. So there it is. Okay. I'm then going to take my ruler, put it at one of my intersection points, rotate it so that it goes to the other, and draw a segment. Okay, so if I measure this now, so I put my ruler right at A, and I measure to my perpendicular bisector, it is 3.1 centimeters or 31 millimeters, and the full length is 6.2 or 62 millimeters. So that's half, and that's half. So there's my perpendicular bisector. We need to do that for all three sides. Okay, so I'm going to bring my compass, and I'm going to put the point at C. Holding my breath as I do it. Okay, so then I do this, I open it up. Now I want to draw a circle centered at C, radius CB, which is right here. Flip my compass over, center my compass, put my compass at B, Alright, okay, centered at B with a radius of BC. Okay, so this is going to get a little messy, so let's find color coding. And then I'm looking for the intersections of the two greens now. So there's one, and the other one is way down here. So I'm going to put my 0 here, because that's how my ruler rotates, from 0. And it's right about there, and then I draw a segment. Whoops, Wrong point. How about the green, green, not green, red intersection? Green, green intersection, rotate to green, green intersection. Okay, just bear with me here. Right about there, and draw a segment. Okay, do this one more time with blue. Now we're going to draw a perpendicular bisector of AC. So I put my compass point at A. Rotate my compass so I'm at C. Right about there. And draw a circle. Flip it. Put my point at C. Radius A, draw a circle. Done with my compass. Look for my blue intersection points of my two blue circles. Blue circles are here, and when I rotate this, I put my ruler here, rotate to about there, and draw my segment. So notice what just happened there with this mess. Here's my red perpendicular bisector of AB. Here's my green perpendicular bisector of side BC, and the blue is the perpendicular bisector of side AC, and they all intersected at the point, the same point right here. Change that to black. Right here is where all three of those perpendicular bisectors intersect. So I'm not inside the circle, but that is the point of concurrency, so it's not an orthocenter in this case. All right, it is just point of concurrencies. Alrighty, so it says, how did using this tool differ from using a compass and a straight edge? Compare your construction with that of your partner. Did you obtain the same results? Okay, that's just an open-ended question. I can't answer that for you, but we're going to continue on to the exploratory challenge. And it says, when three or more lines intersect at a single point, okay, we had three lines here intersecting at a single point. Three is three or more. They are blank. Well, that's the definition word, concurrent. And the point of intersection is the point of concurrency. So we just defined the name of this lesson. Okay, 2 R's. I always forget that. Point of concurrency. So let me just convert this to text. Okay, that's a little bit better than my chicken scratch. There you go, point of concurrency. So you saw an example of a point of concurrency in yesterday's problem set, which was problem set lesson 4. And in the opening exercise today, when all three perpendicular bisectors pass through a common point. The point of concurrency of the three perpendicular bisectors is the okay, another definition, circumcenter of the triangle. Okay, page 2 brings us to a diagram where it's giving us a triangle ABC with a point P. The circumcenter of triangle ABC is shown below as point P. The questions that arise here are, why are the three perpendicular bisectors concurrent? And will the bisectors be concurrent in all triangles? Recall that all points on the perpendicular bisector are equidistant from the endpoints of the segment, which means the following. P is equidistant from A and B, since it lies on the perpendicular bisector of AB. Okay, B. P is also blank from B and C, since it lies on the perpendicular bisector BC. So we want this word, equidistant. Therefore, P must also be equidistant from A and C. Hence, AP, if we drew a line segment from A to P, so let's do that. So I want to show you that this is true. Let's use red. So if I draw a segment from A to P, there it is. Oop. So AP equals BP. Well, is that true? Let's take a look. I am going to, let's see, can I save this? Yeah, let's copy it. But I don't want to change its properties. Okay, I can't do it with that segment piece. I'll have to do it with the ruler because I can't rotate those without changing their lengths. And that's what I'm trying to do here. So what I'm going to do is draw a line segment, or I could just take my ruler and measure all these lengths, but if I take a line segment and draw it from A to P, like so, get rid of my ruler, rotate this and move it then it will show that from B to P is the same distance. Let me rotate it a little more, right about there. Okay, so B to P is the same distance, and then again if I rotate it and bring this down here, rotate it a little to get it to line up. P to C is equal. So this says AP equals BP equals CP, which I just showed you with the same length of segment. So this suggests that P is the point of concurrency of all three perpendicular bisectors. Okay, you have also worked with angle bisectors. The construction of three angle bisectors of a triangle also results in a point of concurrency, which we call the, and I already gave that to you in the definition. I don't know if you remember, there's two words for it, but we're going to use this one. Incenter. It's also orthocenter, but we'll get to that later. Okay, so incenter. Okay, page 3 brings us to another diagram, triangle ABC. It says to use the triangle below to construct the angle bisectors of each angle in the triangle to locate the triangle's incenter. So I'm going to put my compass at point A. Do you remember how to construct an angle bisector? We draw an arc, like so, from A, and then we put our compass on one of the, we put our compass on one of the intersection points of our circle and the two sides, and then we construct another arc inside like so, and then I bring this up here, put it here, whoops, undo, I changed the size, all right, rotate and draw. So there it is, and then I take my ruler, let me put it right at 0 so I can rotate it up to my intersection point, draw a segment through, there's my angle bisector. So if angle A was 40 degrees, this angle I just formed below here is 20, and this angle up here is 20, two congruent angles. I'm going to leave all of my marks while I do this. I'm just going to change colors for each vertex. So now I'm going to put my point at B. Or try at least. Okay. Okay, so I have point B here. I will open this up a little bit. I need to create an arc that will go outside, so I'm going to cross AB and BC. So I'm going to draw an arc like so until my circle intersects both sides. Then I move my compass to one intersection with the circle and a side. I like to shorten this up a little bit. Form an arc. Bring my compass to the other intersection of circle and side. Form an arc. And then where those two arcs intersected, I'm going to bring my ruler. I put 0 right there, rotate it so that B is there, and then draw a line or a ray that will bisect angle ABC. So now this angle is congruent to this angle. So there's my second angle bisector. Going to do it one more time for angle C. We're going to bisect C. So first I put my compass on here. Let's open it up a little bit. What's going on? Oh, over here. Try there. All right, so I want to draw a segment or a segment of a circle or an arc that is actually going to cross AC and BC. So let me shorten it a little. So I need an arc that goes through both sides that form that angle. Then move your compass to one of those intersections. I like to shorten this a little bit. Okay, rotate it around without drawing. Okay, so I'm in the triangle. Draw an arc like so. Move it to the other intersection point. Draw an arc like so. And then bring my compass or my ruler over, put it right on C, rotate, go through that intersection. That doesn't look right. What did I do? Oh, it's right here. All right, so look what I just did. I drew an arc right here, but then my compass wasn't open far enough for my two circles to reach, and I need them to cross. So I'm kind of glad I did that to show you what will happen if you don't have your compass open far enough. So I'm just going to undo, undo, undo. You need to open it up far enough for it to intersect when you draw your circle. So I'm going to draw an arc like so. When I'm on here, actually. So put your compass point on your intersection of your circle that you formed when you had the point centered at C, the vertex. All right, let's try this again. I'm going to draw an arc out here, like so. I'm going to take my compass and bring it over to the other side that forms that angle, BC. Put it here, rotate my compass around, and I want to draw an arc where those two circles cross, which is right here. Okay, so if you don't open your compass up far enough and make a circle with a large enough radius, then you're not going to, these two circles will not intersect, they won't reach. So then I rotate this around and I draw a line segment through. Let me get that a little closer. And I draw a segment here. Okay, so this is a little difficult to see, so let me erase all my circles. Okay, so I got all of those arcs out of the way, and look what happened. When I drew angle bisectors of all three angles, they all crossed inside the circle at the same point, right here. So using the triangles below, we just constructed angle bisectors, and we found the location of the incenter, which is pretty cool. Let's answer these steps now. State precisely the steps in your construction above. Okay, so we don't need to say put your compass on point A, make an arc, blah, blah, blah. We've already defined how we do angle bisectors in lesson 1 or 2, I can't remember which. So all you really have to say here is construct the angle bisectors of angle A, angle B, and angle C, which we did. That's the blue, red, and green line segments. Then 2 says label the point of intersection, Q. So I have not done that, so let's do that. So here is Q. Okay, E says, earlier in the lesson, we explained why the perpendicular bisectors of the sides of a triangle are always concurrent. Using similar reasoning, explain clearly why the angle bisectors are always concurrent at the incenter of a triangle. I'm going to let you try that, pause the video, see if you can come up with it, and then I'll give the answer. Okay, so here it is. Any point on the angle bisector is equidistant from the rays forming the angle. So in other words, if I just pick any point on this blue angle bisector of A, if I pick this point right here, if I put a point right there, any point on the angle bisector is the same distance from the rays forming the angle. So if I now measured how far it was from, actually be perpendicular, how far it was from here to here, and how far it is from here to here, they would be equal. Therefore, since point Q is on the angle bisector of angle ABC, point Q is on the bisector of ABC, that's the red segment, it is equidistant from ray BA and ray BC. Similarly, since point Q is on the angle bisector of angle BCA, angle bisector BCA is the green segment, it is equidistant from ray CB and ray CA. Therefore, Q must also be equidistant from ray AB and ray AC because it is a point on A, the ray that comes out of A that bisects angle A, the blue segment. Okay, since it lies on any angle bisector of angle BAC. It lies on the angle bisector of angle BAC. So Q is a point of concurrency of all 3 angle bisectors. Okay, page 4 brings us to this diagram F. And it says to observe the constructions below. So looking at point A, they're talking about this point here. And it says point A is the blank of triangle JKL. So if you look here, this red line here, or segment, is the perpendicular bisector of KL. This one is the perpendicular bisector of side JK. And this one is the perpendicular bisector of side JL. So we have 3 perpendicular bisectors intersecting at the same point. It's outside the circle, just like in page 1 of this lesson. And so point A is the blank of JK, triangle JKL. And it is the circumcenter. Okay, notice that it can fall outside of the triangle, which it did here. Okay, so what we haven't done yet, and I want you to take a look at this, is... Okay, it's going to say it, so let's keep going. Point B is the blank. So in this circle, we took angle bisectors. So this segment is the bisector of angle S, this one is the bisector of angle T, and this one's the bisector of angle R. They all meet at the same point inside this triangle. So think of inside being the incenter. Okay, incenter. There we go, incenter. Delete that. Okay. The circumcenter of the triangle is the center of the circle that circumscribes that triangle. So what's really cool about this is if I construct 3 perpendicular bisectors of all 3 sides of a triangle and find the circumcenter point outside here and take a compass and put it on point A and then over to one of the three angles of the triangle and draw a circle, then it will hit all three angles, and when a triangle's vertices, all three, are on the surface of a circle, the edge of a circle, then that is called circumscribed. Okay, so on a separate piece of paper, draw two triangles of your own below and demonstrate how the circumcenter and incenter have these special relationships. So that's something you can do on your own. And now G says, how can you use what you've learned in exercise 3 to find the center of a circle if the center is not shown? Okay, so it says, inscribe a triangle into the circle and construct the perpendicular bisector of at least two sides. Okay, so I can't just assume this to be true. I want to check it. Hopefully you are that inquisitive as well. You want to know for sure. So it says, how can you use what you have learned in exercise 3 to find the center of a circle if its center is not shown? So I'm going to draw a circle. There's my circle. Move the compass. Now I don't know where the center is, right? So the answer said, inscribe a triangle into the circle and construct the perpendicular bisectors of at least two sides where the bisector intersect in the center of the circle. So now I'm going to take my ruler and a line segment that goes from the edge of a circle, like so, over to the other edge of a circle, like so, is called a chord. So there is one side of a triangle. So now if I just pick anywhere else on the circle, such as right here, and rotate my ruler to there, and draw a segment over to here, and then move my ruler, to here, and finish this triangle. Okay, so there is a triangle circumscribed in this circle. Vertex A. Here's my pen. Here's A. Here's B. And here's C. So we inscribe the triangle in the circle. Done. And now construct the perpendicular bisectors of at least two sides. So let's change the color of our compass. Bring this over. How do you do a perpendicular bisector? Put the point at one end, open your compass up to the other, draw a circle. Okay, do the same from the other side. Take my ruler, construct a segment. Okay, put that right there on 0. You have to have patience when you do this. You need to be extremely willing to snapping. I don't want it to snap. Let me see if I hit Alt if that stops the snap. No. Shift. No. Control. No. Okay, the problem with my ruler is it's snapping to perpendicular. So let me rotate this and see if I can get it this way. Okay, let me just try this. I don't want 90 degrees, I want like 89. And it won't let me. See that? Okay, so we're going to just do as close as we possibly can to this. So if I rotate this, we're off a little, I can't do it, there we go. And then if I do the same, let's now change my color to red, or how about purple, because we have a red triangle. Okay, so now I have my compass centered at B, radius BC, and I'm going to draw a circle. Okay. Then I rotate it around, centered at C, same radius, draw my two circles, get this out of the way, put my ruler on my bisector, or my intersection of my two circles, I should say, to form my bisector. Rotate it so that it goes through the other intersection point and extend it beyond. Okay, I just found the center of circle ABC right there. That's what this is saying. So in order to find the center of a circle, you can simply draw a triangle inside it. Find two perpendicular bisectors. Where they intersect is the center of the circle, because the point, which is out here, is going to be the same distance from B and C because it's on the bisector, and it's going to be the same distance from A and B because it's on the bisector, so therefore those distances are radii. Pretty cool stuff. Page 5 brings us to the end of lesson 5. Go to your problem set.